Okay, welcome back, grade 12s, to electric fields number 4. And today we're going to be talking about point charges, and specifically we're going to be talking about point charges in terms of scalar quantities and vector quantities, and how we deal with both of them. So, if you recall, when we dealt with planets and stars, remember that we didn't need to think about where the surface of the sun was or where all the mass was located. When we were calculating force, field, energy, potential, all that stuff, we just had to consider a star as being a point mass. And the question is, can we do that for charged objects as well? And the answer is yes, we can. So when we're thinking about a charged object, say a big spherical Van de Graaff generator, we can think of the charge as being held sort of in the center of that sphere, of the Van de Graaff generator. So by now, this is quite familiar to us. We've got our square. Oh, that went weird. We got our square, and we have our 4 quantities that we're all used to dealing with by now. And those 4 quantities are potential up here, potential energy, field, and force. And our formulas, again, all of these are going to start with the letter K, the K, Q1, Q2. These ones will just have Q, these ones will have Q1 and Q2. And potential and potential energy, these are both over R, and field and forces, these are going to be over R squared. So if I want to know what the force is, I know it's going to be K, Q1, Q2 over R squared. So that's how we can determine it. And just as before, we can convert between these quantities just by realizing, okay, if we want to go from force to potential energy, we would need to multiply by the radial distance, or likewise, going from potential energy to force, we would divide by radial distance. Same thing for going from potential to field, we would just divide by R, or multiply by RE times R is going to give us V. And for these ones over here, if we want to know what the force is, it's going to be E, and we're going to multiply that E by Q to give us force, or this way here, we can take the force and divide it by Q, and we're going to end up going to field. So we can see how these quantities are related again. We can say F equals Q times E, or E equals the force given per charge, F over Q. So we've got those relationships there. Now let's try and figure out, or of course we can always just use the formula. So F equals K Q1 Q2 over R squared, and E is just going to be KQ over R squared. So let's try this question here. Please pause the video in a moment when I stop talking and try this calculation for yourself. So calculate the electric field strength due to the nucleus of charge plus 82E. So E, just as a note here, this is our fundamental unit of charge. So the charge of an electron, or the amount of charge an electron or a proton would have, is often referred to as E. And again, just as a reminder, if you haven't memorized it yet, this is the amount of charge in the fundamental unit of charge, 1.6 times 10 to the negative 19 coulombs. So if you have a nucleus with charge of plus 82E, it just means it's 82 times this value up here, and it's going to be positive. And if you've forgotten this unit here, nanometers, just remember, again, with this unit, we use a lot of very, very, very small numbers. So milli is times 10 to the minus 3, micro is times 10 to the minus 6, nano is times 10 to the minus 9. Nino for nano, easy to remember. Okay, pause the video now, try this question for yourself. Okay, if you're back from the video, or back from pausing the video, and hopefully you've answered this question for yourself, let's take a quick look at solving this one here. So we are going to be finding out the field, and we know the field strength is KQ over R squared. So we're just going to multiply those values together. We already have all of these, so this is going to be 9 times 10 to the 9 times 82 times 1.6 times 10 to the negative 19, and we're going to divide that by 0.35 times 10 to the minus 9 all squared. And this is what we get from that. So 9 times 10 to the 9 multiplied by 82 times 1.6 times 10 to the minus 19. And I'm going to divide that by 0.35. We just put this in brackets. 0.35 times 10 to the minus 9 squared. And that's what we get. So the answer that we're looking for here is, what's the field strength? It's going to be 9.64 times 10 to the minus 11. Actually, it should be 2 sig figs, so 9.6 times 10 to the minus 11. And units for field, well, we have 2, but in this case here, it makes more sense to say newtons per coulomb, because we're dealing with force, and so it makes sense. The other unit, you can recall, is going to be volts per meter. We typically use this one a bit more when we're dealing with parallel plates. Okay, and let's look at this question here. So what do we do if we want to calculate the field strength when there are 2 or more charged objects? Well, let's give 3 different examples here and see what they look like. So let's look at example number 1. We've got a positive charge here and a negative charge here, and they're both, actually let's do this. Let's make this one a positive, and this is the point over here. So this is our point P, where we're calculating the field. So in this first example here, both of these would exert a field away from the charge. Recall that positive charges point away, the field points away because it's telling us where a positive charge would go, and negative charges point towards because it tells us, again, where a positive charge would experience a force. So in this case here, from charge number 1, it's positive, the field's going to be this way. From charge number 2, it's also positive, it's going to be this way. So if we wanted to figure out the potential, we would need to add both of these together. So if we think of these as vectors, there's 2 vectors pointing to the right, so we would have this vector plus this vector, and that would equal this longer overall vector. We're just doing vector addition, but it's an easy case where they're going in the same direction. What about if we look at example number 2 here, where we have 2 charges, but the fields are in the opposite direction? So if the point is right here, well then, from this charge on the left, the field's going to be to the right, and from the charge on the right, the field's going to be on the left. So if we're adding these 2 points up, we're going to add this vector plus this vector. And in this case here, I've drawn them to be the same distance, and we're assuming they're the same size, so this is going to be 0 field. But it could be something like, for example, if I drew this one closer over here, then it'd be a larger force to the left and a smaller force to the right. So it doesn't always cancel out, obviously, but it kind of did in this example here. But if it didn't cancel out, we would just have something like this large one plus this smaller one is going to equal this kind of reduced size one. So again, we're just adding vectors, but it's an easy vector addition because, again, they're all on one axis. They're all on going along the x-axis or the y-axis, whatever it is. Okay, what about example number 3? So now example number 3, we've got charges that are acting at right angles. So let's say I've got a positive charge here, and let's say I've got a negative charge over here. Let's mix it up a bit. And this is my point right here. Well, what is going to be the direction of the field from this charge right here? Well, we know it goes away from it, so the field from this charge is going to be in this direction here. And if we're looking at this charge here, we know that fields go towards a negative charge, so this one is going to be going downwards. So now we have 2 charges that are kind of at right angles to this point right here. So what is going to be the overall direction? Well, this is another case of vector addition like we've done before, like you've been doing for 2 years in physics, where let's say you have a force to the north and a force to the west, and you'd have overall a resultant force that's somewhere northwest. Well, this is the same thing. These are just 2 vectors that we're adding up together. So in this case here, it's going to be a vector like this. And when we add vectors, we remember that we do them tip to tail. So we would add another force or another field going downwards, and this would end up looking like this for this field plus this field equals this resultant field right here. Didn't draw that very well, but yeah, that's the E resultant. So if I call this E1, E2, and the E resultant or E total is going to be somewhere to the southeast, if this was north being the top of the screen, for example. So we have now seen all three examples that we'll be dealing with. Now let's try some example problems. So this first one here, this is all in one dimension. What the question is asking is there any place where there would be overall zero field strength? So to solve this, we kind of need to think about dividing this area into three regions. So I'm going to call this region A, region B, and region C. Now, is it possible that in any of these three locations, we could draw a point? So maybe I could draw a point here, where if I add those two field vectors up together, it would add to 0. What about in B, or what about in C? So think about what I've done in examples 1 and 2 above. Think about the direction of the fields from these two charges. One of these is -2, and one of them is +1. Is there somewhere in any of these three regions where there would be 0 field strength if we add up the two vectors? So pause the video here, take some time, think about this problem, and then we'll come back to it. Okay, so if you're back, let's take a look and see what the solution is. So we can try all three of these regions. Let's try region number 1. So we know that this is a negative charge here. And so from this first charge here, the field on this is going to be towards it. And because it's very close, and because this is a, actually we'll get to that in a second. So this one here is going to be going towards it. And from this charge over here, there's going to be a field that points away from it. Now, which of these is going to be a stronger field? Is it going to be this field that's pointing towards the larger magnitude charge and it's closer? Or is it going to be the one that's moving away from the smaller magnitude charge and is further away? Well, hopefully you can see right away that out of these two fields, this one is going to be A, it's closer, B, it's a larger charge, it's 2 nanocoulombs instead of 1. So this is going to be a very large attractive force and a very small repulsive force. So overall, could it be 0 here? Well, based just on the signs, you wouldn't be able to tell. Or sorry, based just on the values, you wouldn't be able to, based on the size, the type of charge, so positive or negative, you wouldn't be able to tell. But based on the size, you can determine that this force or this field to the right is always going to be the bigger of those two compared to this repulsive force from the positive charge, so it wouldn't work out here. Now if we look at part B, this is a negative charge, which means it's going to be towards this here, and this is a positive charge, which also means it's going to be towards here. Could we add up these two vectors anywhere in here and get 0 field? No. So in this case here, it's always going to be some force, some overall field to the right. Large right, small left means overall, it's going to be a field to the right. Here, no matter what we do, it's always going to be kind of a larger field to the left. These are always going to add up, and so it'll never be 0. You can't get it to be 0 here. Now let's look at part C here. From here, part A, this negative charge here, I should say, on the point C here, the negative charge is going to be a repulsive force. So that's going to be moving to the right. Oh, pardon me, I made a mistake again. So from the -2 nanocoulomb charge, that'll be an attractive force. So that's going to be pointing this way. And from the 1 nanocoulomb, that's going to be a repulsive force. So that's going to be this way. Now, this one here is less charge, but it is closer. This one here is more charge, but it's further away. So you could prove this to yourself. If you wanted to give an example distance here of let's say these two were 1 meter apart, it is completely possible to show that it would be you could have a point here where it'd be 0 point, or sorry, it'd be 0 field strength. So these two vectors, one's going to be smaller magnitude but closer, and the other one's going to be larger magnitude but further away. So it is possible to have 0 field here. So not in the first two, but yes in the third one there. Sort of a tricky problem to think about, but yeah, it's definitely solvable. Okay, what about this one here? What's the field strength at point X? So please pause the video here. It is going to take a few minutes to solve this one, so pause the video, try and solve it for yourself, thinking about the fact that we've got what are the direction of the arrows from this positive charge, what are the directions of the arrows from this negative charge, keeping in mind the distance here, to calculate the overall resultant field strength. So pause the video now, and we'll come back and solve it when you're done. Okay, well, if you're joining us again, let's take a look at this problem here. Okay, so we're trying to find the field strength. We know the field strength. I'm going to call this A, and I'm going to call this B just for the purposes of this video. So field A is going to be KQ1 over R squared, or I'll call it QA, and field B is going to be K times QB over R squared. So we can calculate what these are. So let's just do the math on this one here. So for A, we have K times Q, and we said it was, let's see, 1 nanocoulomb. So times 1 times 10 to the minus 9, divided by R squared. Now R, we said was 3 nanometers. So divided by 3 times 10 to the minus 9 squared. And that's going to give us a field of 1 times 10 to the 18. Now what is the direction of the field from A at this point here? Well, this is a positive charge. We know that field represents where another positive charge would go if you put it here. If I put a positive charge here, it would move in this direction here. And so that's going to give me a field strength of 1 times 10 to the 18 newtons per coulomb. Okay, let's try B. So in this case here, we have 9 times 10 to the 9 multiplied by QB, which is 1 times 10 to the minus 9. That's our Q. And we're going to divide that by R squared. The R in this case is 2 nanometers, so we're going to divide by 2 times 10 to the minus 9 squared. And that's going to give us here 2.25 times 10 to the minus 18. And what will be the direction of this field from B? Well, this is a negative charge, so we know this is going to move in this direction here, and this will be 2.25 times 10 to the minus 18 newtons per coulomb. So we've got our two field strengths here. Let's add them up. Well, we have this vector in this direction here, 1 times 10 to the 18. We've got this vector here, 2.25 times 10 to the 18, and we're trying to determine what is our overall resultant force or resultant field going to be. So this is our resultant field. Well, we should be able to solve this now. We're going to be just squaring both sides of these to find the answer using Pythagoras. So 2.25 squared plus 1 times 10. Oh, sorry, these are, to the 18, not negative 18 here. Okay, so 2.25 times 10 to the 18 plus 1 times 10 to the 18 squared, and take the square root of that. Oops. And that's going to give us 2.46. So this is going to be 2.46 times 10 to the 18 newtons per coulomb. Okay, so now we've got our overall magnitude, which is this right here. And we need to find also, because it's a field, we need to know the direction. So for the direction, we can just use sine or cos or tan. In this case here, we would use tan would be the easiest one here because we have the sig fig. So 2.25. Now I'm going to just be lazy. I'm going to ignore the 18s because if I take this divided by this, the 8 times 10 to the 18s will cancel out. So 2.25 divided by 1 is going to be our value there. I'm going to take the inverse tan of 2.25, making sure that I am in degrees. And that's going to give me 66 degrees. So this theta here, so theta equals 66 degrees. I'm just going to say below horizontal. Okay, so this seems new, but it's not new. We've been adding vectors for many months, or for a couple of years now at least. You've been adding vectors together, and so this is just one more example of adding two vectors together. Now the other question I have is, what would be the force acting on an electron that we placed at x? So what we know is, at this point here, at this x, we know that the field strength is 2.46 times 10 to the 18 newtons per coulomb at 66 degrees below the horizontal. So what would be the force if I were to put one electron here? What would be the force, the magnitude, and the direction? So pause the video here, try and solve that. Again, just a reminder, the charge E is 1.6 times 10 to the negative 19 coulombs. So try solving this question here based on the previous information. And pause the video now to give that a shot. Okay, well, if you're back, let's try and solve this one. So remember that, actually, before we get into the direction, let's just talk about the value here. So we saw before from our square or from our previously given formulas, if we want to know the force, it's just going to be Q times E. So easier than you probably thought it was going to be. In this case here, the Q is going to be 1.6 times 10 to the negative 19 coulombs. And the E is, well, we just solved that, 2.46 times 10 to the 18 newtons per coulomb. So it's this many newtons per coulomb times this many coulombs gives us this many newtons. So let's solve for this one here, 2.46 times 10 to the 18 multiplied by 1.6 times 10 to the negative 19. And that gives us 0.39 newtons. So that's going to be the force acting on the electron. Now the follow-up question to that is, what direction would it be? Well, here's where you have to think about what a field line really represents again. So we know that a field line represents the direction that a positive force would experience a force, or where a positively charged particle would experience a force. So for example, if I were to put a positively charged particle at this point x, well, I know that a positively charged particle would move in this direction here. So if a positively charged particle would move down and to the right, or 66 degrees below the horizontal, what direction would a negative charge move? And the answer is the exact opposite direction that a positive charge would move. If a positive charge goes right, a negative charge goes left, etc. So in this case here, the direction is going to be this direction here, and that's going to be 66 degrees, I don't know, above the horizontal to the left. So if you drew out this diagram in a test question, for example, that would be just fine to leave it as this diagram here. This would be the direction that the electron would flow, or would move in this example here. So that would suffice to describe it. And that, so just a point to remind you is that electrons, or negative charges, move in the opposite direction to where a positive charge would go. Okay, so here's the question I have. So far in all these examples that we've done, and including the last few weeks, how we've dealt with polarity when we're dealing with these vector quantities. So what I mean is when we have a formula like either k q over r squared, or f equals k q1 q2 over r squared, in both of these cases here, we didn't really take into account the polarity. What I mean by that is positive or negative aspect of the charge. We didn't really take that into account when we were doing our calculations, did we? So for example, if we look at the previous example, there's a positive and there's a negative charge here. Well, we didn't really, when we did the math on this problem here, we didn't put a positive Q in there and a negative Q in here to determine the direction. We just looked at that as a vector and said, well, this one's going to be going to the right and this one's going to be going down. We didn't really put the negative into the formula at all. And the reason for it is that it's just really more confusing than it's worth. We don't need to put in a negative sign or put in two negative signs for force or whatever it is to determine what direction it's going to be. We know that from understanding what positive and negative charges do. We know positive charges repel, we know negative charge or opposite charges are going to attract, and same like charges, two positives, two negatives, those are going to repel each other. So we don't need to put that into our formula to figure out the direction. So we're just doing vector addition. So we didn't put the negatives into the formula, we just said, okay, it's this arrow plus this arrow gives us this overall arrow. So we ignored it. So for this part here, how do we deal with polarity of charges? Ignore in calculations. Just consider direction of vectors. So the negative or positive is not a part of our calculation. It's just a part of determining what direction we're going to draw the arrows. Are we drawing it away from a charge or towards a charge? So what about for scalar quantities? Well, for scalar quantities, what I'm going to tell you is do not ignore polarity. So let's look at a simple example first. Let's say I've got a positive charge. We know that around a positive charge, we have a positive potential. And we gave the example in your assignment that you had a few weeks ago, we gave the example where we looked at this, and this is kind of like, if we look at this from the side, if we were comparing it to gravity, it would be like having a mountain that kind of asymptotically goes towards infinity. And so at this point here, we might have 100 joules per coulomb for gravitational potential. Remember, potential is how much energy you're going to have if you were to put a charge here. So if I put a +1 charge here, it would have 100 joules of potential energy being this far away. So again, this would, from the top view, this would be like 100, this might be 50. So we're saying at this distance away from this positive charge, a 1 coulomb charge would have 100 joules of potential energy. And likewise, if we go a bit further out, we're going to have 50 joules of energy. So if we're looking at our equipotential lines from the top, they look like this diagram. If we're looking at it from a side view and kind of imagining it's just like gravity, that's going to be this part here. So we're saying if we're this distance away, we're going to have 50 joules of potential energy for every coulomb. And it will be a positive, and so around a positive charge, the potentials are always going to be positive as well. If I put a +1 coulomb charge here, it's going to have 50 joules of potential energy. Okay? Now, this is very different from a negative charge. If we look at a negative charge, let's do it in a different color here. If we do this as a negative charge, then we're going to have the same equipotential lines, but this might be -100, and this might be -50 joules per coulomb. And if we were going to look at this as kind of a side view here, it would be like a negative mountain, I guess. I don't know what you'd call that. A big ravine. And again, if you have a negative charge here, if you're at this height here, you might have -100 joules per coulomb. So if I were to put a +1 coulomb charge here, it would have -100 joules of potential energy. So this would be the line representing 0 joules per coulomb. That's kind of our ground level. Same thing with this. This is going to be our ground level. And we see with a positive charge, you're going to be above ground, so you're going to have positive energy. And if you go here, you're going to have negative energy, or negative potential energy for every coulomb that you put here. This might be -50 joules per coulomb, etc. So when you're calculating this, you will have to take into account the polarity. Remember, this is potential energy and potential. They're both scalars. So there's no arrows involved. We don't have potential to the left or potential to the right or potential energy up or potential energy down. We just have a physical number, 50 joules, 100 joules. There's no direction accounted for in that. So we can't ignore polarity. We do need to include it in your calculations. And you'll see why that would be, and why it's a little bit different than dealing with vectors. So vectors we just figured out from the arrow, and scalars we don't. So thinking about that, I want you to try and answer this example for here. Two charges, plus Q and plus Q, fixed in space. What's the value of the voltage, or potential, and the electric field at this midpoint? And we're assuming, as always, that the potential is 0 at infinity. So pause the video here, and I want you to think about this. Which of these is going to be which of these four answers is the correct one? So pause the video here, and come back when you've thought about it and you think you have your answer. Okay, so let's take a look here. When you are adding vectors together, so let's say we're trying to solve our field, we add these up as arrows. So from this charge on the left, there's going to be a field that goes to the right. These are identical charges, and this is the midpoint. So we know the distance is the same, we know the charge is the same. From this charge on the right, we know we're going to have a field that points to the left. And so if you add up one vector to the right and an equal and opposite vector together, we're going to have 0 field. So in this case here, the electric field is 0, which means that it can't be this one here or this one here. Now what about potential? Now when we're dealing with potential, we're not adding vectors, we're adding scalars. So this value here, the potential here at this midpoint from this charge on the left is going to be, actually let's just go even more high level. If we want to know the total potential, this is going to be potential from the left charge plus the potential from the right charge. In this case here, the potential from the left charge is going to be kq over r. The potential from the right charge is going to be kq over r. So if we add these two together, we have 2kq over r. Now r is not 0, k is not 0, 2 is not 0, q is not 0. So could this total potential possibly be 0? And the answer is no. So you do need to include this overall charge in your calculations by including it as q. So let's change the question slightly. Let's make them, okay, so the answer for this one here is that voltage is non-zero. Voltage is going to be equal to 2kq over r, but the electric field is 0. Now let's take a look at a slightly different scenario. Let's say I've got plus q and I have minus q. So let's look at the field. So for the field, we're going to have a repulsive force to the right from the one on the left. So again, I can do the same thing. So E total is just going to be E1 plus E2. Remember that we're doing these as vector addition. So E1 is going to be a field to the right. E2 is going to be an attractive field because it's a negative charge. It's also going to be to the right. So if I add these two vectors, it's just going to be a very strong field, twice the size of the other ones, going to the right. So in this case here, the field would be non-zero. What about for potential? Well, for potential, V total is going to be V1 or V left plus V right. This is going to be KQ over R, and this is going to be K times negative Q over R. Let's add these together. We have K, so equals KQ over R. I'm just going to move the minus sign outside, so minus KQ over R. And what is this total amount going to be? Well, this is going to be 0. So in this case here, our total potential is going to be 0 for this scenario here. And that works only because I didn't ignore the signs. If I ignored the signs in here, my answer again would have been 2kq over r, and that would have just been wrong. It wouldn't have been correct if we ignored the sign. So when we're dealing with potential or potential energy, we have to include the signs in our calculations. If we don't, the answer will be wrong. In terms of the calculations for potential, I did not include the sign in my calculation. I just figured out the magnitude. It's going to be kq over r squared, and then I took into account what the direction is going to be. So both of these would be kq over r squared, and they would both be to the right. So my direction or my sign wasn't included in my calculation, it was just included in my drawing of my vectors. When I dealt with a scalar quantity like potential, you have to include the sign. And we'll just do one more example here. So for negative q and negative q, can you tell me what would the potential would be? Let me just redraw this here. What would be the potential and the field at the midpoint here? So pause the video, see if you can figure it out for yourself. Okay, so let's come back to this one. So I'm going to just move this information over here. So for this point here, from this charge here, so my total E is going to be E left plus E right as vector addition. The E to the left is going to be an attractive force, that's going to be this, and the field from the right is also an attractive force, it's going to be this. If I add these two vectors together, I get no overall field, so the field would be 0. What about for the potential? Well, potential total is potential 1 plus potential 2. Potential 1 is going to be negative kq over r. I guess I can write it this way. K times negative q over r, which I just changed to kq over r. I'm going to add k times negative q over r again, and this is going to give me negative 2kq over r when we add these two together. So if I knew the value of k, let's say k is 9 times 10 to the 9, and let's call this 1 meter. I'm just going to give you an example calculation here, and let's say the q is 9 nanocoulombs, so it's 9 times 10 to the minus 9. Then this is going to be 9 times 10 to the 9 multiplied by 9 times 10 to the minus 9, multiplied by 2 and negative, so this would be, for example, 9 times 10 to the 9 times 2 times 9 times 10 to the minus 9. Oops. And I'm going to divide that by 1 meter. That's going to give me negative 162. So I should have put the negative sign up here. But that would be negative 162 joules per coulomb. So if I ignored the signs again for this one, I would have gotten the wrong answer. I would have gotten positive 162 joules per coulomb. That would be wrong. That would be very, very wrong. The answer is going to be a negative value. In this case here, the potential is going to be negative because, how do I explain that briefly? Yeah, it's near a negative charge, it's going to be a negative potential. It's lost potential. If we look at this diagram up here, for example, again, we know that it would have been, from infinity being 0, it would lose more and more and more potential, and therefore gain more and more and more kinetic as it moves closer to where the negative charge is located. So it'll be losing more and more and more potential, which means it'll be gaining 162 joules of kinetic. If we had this point an infinite distance away and let it go to fall towards this point here, it would have lost 162 joules of potential, gained 162 joules of kinetic. So hopefully this is making sense. We've got a few sample calculations for you to do this week. Try and do at least 3. If you can do all 5, even better. And you will need this information here about positives and negatives with vectors and with scalars. You will need that to do well on the test. So please pay special note to that. And as always, if you have any questions, I will see you in the virtual fit block or send me an email before then. Thank you.